Okay, all right, great. Well, I'll start. So I guess first I'd just like to say, it's definitely bittersweet moving on. It's been 15 years that I've been here. I've had a really wonderful time. Again, I got here right before the LHC turned on. We got going. The LHC turned on. For those of you who remember, right after it turned on, it exploded, and then there was we had a little bit of time. There was fun projects going back to look at old, like 10-year-old data from the LEP collider and the Aleph experiment that I was on briefly in my PhD studies. And we went back and actually had an opportunity maybe to find the Higgs and archive data, which was pretty exciting. That led to some projects that were, I think sort of emblematic of the nice parts about the CCPP. So we had Itai Yavin, who was a postdoc at the time, and I worked on that Aleph analysis, and that led to some proposals that, like, hey, particle physics community, you should really try to save your data analysis in a way that it can be reinterpreted later. And that's a project that is a kind of a high level thing. And that idea was, many, many years ago now, like more than 10 years ago, I guess. And it's sort of just now happening at the LHC that we now actually have the analysis pipelines preserved in a way that they can be reused and reinterpreted. Patrick, who's here as a postdoc in our group here, is working on that kind of stuff. And then once we have that, that's enabling all sorts of other things. Arena, who's a PhD in data science, is here, and she's working on ways to reuse that to more like efficiently explore the LHC data. I don't know. Also, not to go through down memory lane too much, but it was also a little bit around them. It was like Neil had these exciting ideas about how there could be additional forces and dark sectors and all of the ideas of like dark photons and these things and millicharged particles and all of those related ideas. All that started while I was here. Josh was still a graduate student in Princeton, and that's led to, for instance, entire new experiments like Millikan that Andy's working on that's now being installed at the LHC. So it's been amazing what all has happened. That of course like culminated at one point in the discovery of the Higgs in 2012, which was 10 years ago as of July. So this time 10 years ago was pretty intense. And then after that happened, sort of the first round of measurements of the Higgs properties, which was interesting and exciting. Then the LHC went down for a shutdown. I went on sabbatical, and that was also July 2012 is right when like deep learning started to explode. And so from that time, I spent a lot of effort trying to think about how to use what's going on in machine learning and AI to try to help us do physics. And a lot of that is also trying to remove the sort of mysticism of everything and like really ground it and see it as how a new set of like, in some cases like a new set of numerical techniques, or but really try to cast it in kind of very grounded. Oftentimes it's in a statistical way. And so what I wanted to talk about today is kind of the first set of work that I've been doing, which is really in a new direction, and it's much more in a theoretical physics setting, and it's also much more in a version where you're really getting the aim is to get out like equations, and like something that looks more symbolic as opposed to something more just like kind of purely numerical black box function approximation type of picture of machine learning. So I'll say kind of quickly that in terms of the kind of like AI for physics projects that I've worked on, and kind of so you can see a little bit of an evolution of the types of problems. I'd say the first kinds of problems that are the most like straightforward and the things that people were doing would be sort of like, and here I'm using AI to maybe machine learning is probably a better term here. So I'll maybe machine learning for like it doesn't have to be LHC, but this applies to what I was doing. The LHC sort of data analysis pipeline. Okay, and so here it's things like I have some energy deposit in my detector, and I want to try to say, is that thing an electron or a photon, or I want to like estimate its energy. So these are like classification and regression type problems where the input data is something in the detector, and the output is some sort of label. And so you can think of this as essentially regression. Then there's the next sort of rung up the ladder was sort of machine learning for like statistical inference, basically. And again, in kind of the doesn't have to be. At first, it was in the LHC setting, and so basically, what we were wanting to do was try to estimate essentially the probability of some high-dimensional, high-dimensional data, given the parameters of our theory. And so, this is basically what theory does. Given some parameters of, for instance, masses of particles and how they interact, or effective field theory coefficients, or whatever you're trying. That's what we do in physics with theory, is to try to predict what do we expect the data to look like. When you stick a really complicated detector in the way, this becomes very this is no longer trivial. This is not like pencil and paper calculations anymore. You have simulators, and typically, so if you want to, for instance, simulate one collision at the LHC, there's lots of ways the same scattering of like protons into like some particles, what that will look like in the detector will vary because there's lots of random processes along the way. So when you simulate one collision of LHC data, in the LHC data, there's about 100 million random variables, like calls to like the RAM inside your computer simulation to simulate that thing. And so if you really wanted to do this, you would somehow like need to integrate out all of those random variables to get that, what you observe. And that integral over 100 million dimensional space is like not tractable. So that's where machine learning comes in, is essentially ways to try to estimate this thing. So you can put like a tilde over it or something, trying to estimate this. And this is, you can think of it as the likelihood function. You plug in data, and then you try to estimate parameters, which are like essentially measurements. Those are the measurements of the LHC. So that kind of stuff happened and is continuing to happen. There's been lots of exciting work. As we worked with Sid Visha Sharma, who used to be here. We've worked on extending those kinds of parameters to things related to dark matter and strong lensing and all sorts of interesting problems. The next kind of side project that we did had to do with dynamical systems. And so here, we were doing things like you've got a few planets floating around, and they're all moving around because of gravitational interactions and things. And so it would be something like an in-body simulation. And we would just run this is all done numerically, like in silico. We would run, you would just see how that system would evolve. And we would use a type of neural network called graph neural networks, where the planets would be like nodes of a graph. And then there would be edges between them, which would be something like forces. And then the neural network would essentially try to predict at the next time step, where do you think everything's going to be and how fast will it be going. And one of the things that was interesting there is that we came up, we know that it's a Hamiltonian system, so we figured out how to make neural networks that know that it's a Hamiltonian system and that there's symmetries involved, and they work very well. And then what's nice is that once you've trained a network like that, you can actually apply it to a new system with a different number of planets, with different masses, and things like that, and it will still predict what's going on. So you're getting closer to actually like kind of understanding the physics. But this was kind of a little side project. It was together with Shirley Ho and Miles Cranmer, who's at Flatiron, no relationship. One of the things that was a little bit interesting about that is that later we took, this piece was essentially some black box neural network function, which is not really very interpretable. It's just a function. But then we did something that's called symbolic regression. Where basically you go in the first part, this is all continuous type, the space that everything's working in is continuous, and positions and momenta and etc. And then we went to a situation which is like, can we come up with a formula that will predict, what kind of the interaction here looks like? This is silly because we know what the answer is in these examples, but searching through a discrete space of possible formulas is much harder. It seems like maybe that wouldn't be harder, but when it's discrete, there's no kind of notion of like which direction's uphill or downhill. You basically have to kind of naively just brute force all sorts of solutions, and you get things that look like NP complete problems and stuff like that. There are a few nice approaches, and this is a place where kind of the physics notion of like Occam's razor and simplicity start to come in. You can you can bias the search so that it's sort of searching for simple solutions and etc. So we did that, and we would come up with equations, and then we would recover the actual force laws and things like that, which was nice. And then whichever. So that was the reason I'm mentioning is this is the first place where you see something that's a little bit more like symbolic in nature. And then a lot of work that I've been doing, and this was also together with a group at DeepMind, which is like one of the big machine learning powerhouses. Then the next one that we've been doing now quite a bit to do with has to do with theoretical nuclear physics, aka lattice field theory or lattice quantum field theory / our next paper is going to be for the first time that we actually are able to do real 4D QCD with quarks and gluons, obviously. So this kind of thing didn't have the symbolic feel to it. It's basically, when you do this, your prediction is trying to predict like the expected value of some quantum mechanical operator. When you calculate the expectation, it's like an integral, right? You approximate that integral with things like Markov chain Monte Carlo. That can be very expensive to calculate, and when you get to the physics that you're really interested in, those numerical techniques become very, very inefficient. There's a phenomenon called critical slowing down that happens. And so we were using a type of machine learning algorithm that's essentially good for modeling very high dimensional distributions. And then we use that to try to sample configurations much more efficiently and accelerate this. And we're seeing really big speedups here that are more like parametric types of speedups. Especially here you have things like topological sectors of different things, and it's very hard to sample. And these approaches are working pretty well. So this has been kind of like the flow of projects. But the newest one, which is what I want to talk about today, has to do with AI / ML for amplitudes. Sorry. Okay, so the basic setup here is that we have at LHC, say, we have a detector, particles are flying in, they're going to smash off of each other, and stuff is going to fly out. And for a process like the one I'm showing, it's sort of, you can draw it, equivalently as sort of two things come in, some interaction happens, and three things fly out. Right, that's what's happening. So this is sort of time going that way. If you want to calculate the rate of a certain type of interaction, you have this kind of very high level, the rate is basically equal to a flux, times a cross section. So this has units of area. This is 1 over units of area and time, and this is 1 over time. This is just how many protons you're throwing at each other, per unit area per second or something. And this cross section is something that you can predict from theory. And in particular, this cross section is proportional to some sort of matrix element or scattering amplitude squared, which is just the kind of normal quantum mechanical stuff that you see. And so then the question is that this matrix element or amplitude, scattering amplitude, how do you calculate that thing? Okay. So the typical thing that you would do, okay, here I have a 2 to 3 one, but you would draw Feynman diagrams. So you would say something like, I have a couple of gluons coming in, and then maybe here's a particular process that happens. That's 2 going in, something happens, and 2 going out. I need 1 more. I could get 1 more a few different ways. I could attach it here. I could attach it here, and I could attach it right here. Those are 3 different options. And you would, in the end, you would need to consider all of those and add them all together. And then again, you add them all together to get the total amplitude, and then you square the total amplitude. And they all interfere with each other, etc. So this is the typical way that you would do it is with Feynman diagrams. I mean, the way that I was taught, the way that we generally, there's lots of software that tries to help do this, etc. But there are a few issues here. Is that as you start adding more and more legs, things coming out, the number of diagrams explodes. When you do this, when you draw these diagrams, you can kind of count the number of vertices that are happening, and each vertex, there's like a coupling constant, which is basically saying how something about like what's the chance that this gluon is going to split off another gluon, and so this is related to how strong the fundamental forces are. So you get something like what would be called like alpha strong, or it's related to just like the coupling constant for the strong force, say. And so in this example, you have one, I drew sort of too many things, but okay, there's the two vertices that have to be there. There's the extra one that I need to have a third leg, or if you took it literally here, you count like 1, 2, 3, 4, 5. But so you can count the number of powers of alpha s, and if alpha s is a small number, then ideally you would want to consider all possible diagrams, but it organizes itself as like a Taylor expansion, and that's what perturbation theory is all about, right? So the part of the problem though is that, okay, well if I have confused things by sorry, let me take away my the two different versions. Is that if I want to work in this example where it's like alpha s cubed, I would also want to include the diagrams that look like this with a loop. So something, say like that. So this is supposed to be, there's a kind of a loop sitting here and then things falling out. So this is also alpha s cubed. So I need to consider all of these things. And as you go to, if you want a more precise calculation, you want to go deeper into this farther down in the Taylor series expansion or the perturbation expansion. And so the number of possible diagrams just starts to explode. So maybe you've seen these kinds of pictures before where you have diagrams of all sorts of loops everywhere. And so the number of possible diagrams you can draw, it grows like more than exponentially. It's just there's a tremendous number of them. And as nice as Feynman diagrams are and how they're this kind of pictorial way, one of the problems with Feynman diagrams is that each of these individual diagrams on its own doesn't really mean much of anything. Like they tend to, for instance, they don't have this gauge invariance property. So like interpreting individual diagrams is kind of a fool's errand. So what you really need to do is add them all together, and then that final thing is something physical that's meaningful, that has the properties that you want. But the number of things in that sum is gargantuan. And in many cases, if you do it, you'll see that a lot of them cancel each other out. There's all sorts of additional symmetries and things that are involved, so that when you add all of the diagrams together, you often get a very, very simple result, which is not kind of reflected or manifest in the Feynman diagram picture. Okay. So there's a huge effort, which is not my area of expertise, which has to do with basically, well, can we approach these amplitudes not with Feynman diagrams, but with some other approaches which are more driven by kind of mathematical analysis, analytic properties of functions, various things that don't look like Feynman diagrams, basically. And so there's an entire industry that is making a lot of progress in saying like, well, we basically know, like from the point of view of like an ansatz of what the properties of the function need to be and various constraints, you can kind of zero in on what the solution is. And Lance Dixon, who I mentioned in the abstract if you saw it, he gave a colloquium in the brown bag here not too long ago, and he's one of the like powerhouse experts in this field of amplitudes and etc. So what do I want to? I don't want to get too much into the into that right now. Let me see if I. Let me just think for a second about how I want to organize this. So I think I will come back to amplitudes in a little bit later, but I want to kind of switch gears briefly. But what can I say right now is that in this process of doing it, they have a totally different like set of machinery for trying to calculate these amplitudes. And there are, and when you do that, there are various types of recursion relationships that show up. So that's the and you get into a situation where you sort of, you know, the form, you basically, you have, you know the form of the answer, and very crudely, you know, you're going to be you're looking for some function, you know, that equals like a sum of a tremendous number of like, you know, there's some coefficients here, but this sum can be very large, and then times, you know, I don't know, I'll just write it like fi of x. I'll give more details later. But you sort of know what the form of these possible ingredients are. There's a bunch of coefficients, and also importantly, these things need to be integers. That has to do, those are results that come from the analytic properties that these functions have to have. So in that sense, you could imagine just kind of exhaustively searching through a whole bunch of coefficients here to see if you find the right answer, right? Now you could ask yourself, how do you know if you have the right answer if you've never like computed this thing before? And this is another part which you're just going to take on faith here, is that there are enough things that are known and enough constraints that if someone just if some oracle, you know, if there was some oracle, you know, in the sky that said, I think these are the coefficients, you can check to see if that's the right answer and confirm it. Okay, so you know, so there's, you know, one of those two options happen. So finding this, you know, finding these coefficients is a very hard problem, but checking is easy. And so that's a lot like the nature of the difference between, you know, NP complete problems and, you know, things like that. There are some problems that are very hard to find the solution, but if someone, you know, suggests a solution, it's easy to check.
Why do they call it bootstrap?
I'll try to say, you know, to the best of my understanding a little bit later, but in these recursion relations, there's a way where if you want to describe the scattering amplitude at some high order, you can express the answer in terms of the lower orders, and you basically.
But bootstrap refers to, I'm asking English language question.
Oh, like
does it refer to this Baron Munchausen or something?
Oh,
bootstrap, when he pulled himself with his.
I think roughly, yeah. I think in the sense that.
But what does it have to do with this piece of mathematics? I never understood this.
I guess the idea that you start with something, you know, you're starting with something simple and then you're going to something more complicated, and it seems like you're doing it for free or something. I don't know.
But then everything in science is bootstrap.
Sure, I didn't name it.
But I mean, we can go. There is a historical reason, and but I mean, it would be a little bit longer. Maybe something that we can discuss over coffee, because
so there is no simple answer. That's
well, the answer is maybe simple, but it's long, and the interesting answer is long.
Okay.
Yeah, an interesting one.
Yeah, that's enough.
Okay, I don't know the interesting answer, so I would like to join that conversation.
It goes back to 1968.
Yeah.
Even NYU had something to. I mean, NYU was the anti-bootstrap
that's
stronghold,
right? Not back to
the Alamo of field theory.
Okay, so let me switch gears now, and so we'll come back to the physics side in a second, but now I'm just gonna instead sort of talk about like sequences of integers and patterns, and I don't know, we'll see how it goes. Okay, so I'm gonna just write down some sequences and see if anyone can like tell me something interesting. Okay, so anyone have anything that they want to say about that one? Does that look familiar? Yeah, so that's the Fibonacci sequence. It keeps going. There's a recursion relationship that tells you like what this next coefficient would be. Is it anyone want to guess what that is? Right. So imagine you're a computer and you see. I mean, of course, this is totally underspecified, right? I mean, there's other things that could potentially. This is like the, you know, your gifted and talented tests when you're a kid that are kind of frustrating because it seems like, you know, there's too many possible answers. Okay, but there is some sense in which we all identify it and we know what that one is. Okay, so let me think of another good one here. Okay. Anyone recognize that one?
2 times something squared
The
or
difference.
cubed
the
or
difference-
something.
The difference to the two in sentence.
The difference.
2 times 1 squared, 2 times 3 squared, 2 times 4 squared, 2
Yeah.
times 5 squared.
Yeah, so it's like 2 to the n squared. Yeah, from a physics point of view, do you recognize where that maybe comes from at all?
No,
18? Okay, sorry, that actually, yeah.
no,
What am I doing? Yeah, 18.
yeah, no, that after 2.
Oh, yeah, sorry, I'm just, yeah, I'm sorry, I'm, you know, yeah, sorry. Tricky, yeah, good job. Okay, so you can ask like from a physics point of view, so these also have, you know, different,
See, Kyle, sorry, I have to interrupt you.
Yeah,
See,
please.
this shows the superiority of the human mind. Computer would not guess 2n squared.
yeah, no, exactly, I was gonna say something myself. So this is also like if you were to, I was just wrote that one example down in terms of like number of like states in the nth shell of an an atom or something like that, right? So that was the physics context. So this is one that I actually ran into concretely doing physics, and I had no idea what this sequence was. It keeps going. The numbers get very big very quickly.
Multiplied by 3, multiplied by 5, multiplied by 7, right? You know, there's a page called the Encyclopedia of Integer Sequences.
Yeah, exactly. Yeah. So this one, so there's a website where that I know about where you can type these sequences in, and it does a reverse lookup, and then tells you all sorts of things about them. And so the setting that we were doing where this popped up was that we were looking at how many trees can you put on n leaves. So if you have that's the only one with 2 leaves. With 3, I could do that, or I could do this. It depends on if they're labeled or ordered leaves or not, right? Or there's one where I could do something like, well, whatever. I can't draw, but there's one more where would look like it crosses. Okay, and then if I have 4, there's 15 of them, and we could just count them up. And we were just like, okay, there's got to be some simple formula for like the total number of binary trees on n leaves when they're labeled. I didn't know what it was. I stuck it into this database that Matt just referred to, which is what's it called? The OEIS, I think. And this particular one it has even a number. It's A001147, and the formula is 2 times n minus 3 double factorial. And double factorial basically means you skip one, so it's not like the product of all the numbers, it's that number, skip one, the next one.
That first one, you mentioned the recurrence relationship, but the second one, it doesn't depend on. There's no recurrence relationship.
This one?
The second one, yeah, right. Like with the Fibonacci sequence, it depends on the previous.
Yeah, you could this one here. Yeah, well, it's also this is 2 times, the previous one square root. No, I'm just kidding. Yeah, no, sure. Yeah, I mean, sometimes the recurrence relationship is, is sort of trivial, and then you don't really need to know the other one, where it's like secretly it's in there, but everything cancels out or something. So I guess my point here is like doing physics, we could count these things, but we didn't know what the formula was immediately, and I didn't spot it immediately. Matt picked out the double factorial quickly, but but it can be useful. It's not quite the same thing as what I was talking about, where an oracle tells you the answer and you check, but it's got a similar feel. And so that's partially what I'm getting at here is that when you start talking about AI and this kind of more like mathematical type stuff, sometimes the role of the AI is a little bit more like inspiration or some kind of crutch of some sort that might throw out some example, that there's still probably going to be some human element that's involved, certainly in interpreting it and etc. But it can also be very, very handy. So there are some things that are going on now also, for instance, in terms of like protein folding and stuff like that, where AI is trying to help you give it a sequence and it says, I think this is the shape of the protein. It's maybe not always right, but it's still very helpful in like searching through possible scenarios of where you should put your emphasis and etc. Okay, so then, so the current state of the art on the amplitude side is that they can calculate all these coefficients for one particular scenario, which is fancy n equals for super Yang-Mills theory, where they're looking at gluon scattering, and you can do it for different numbers of gluons, but for the 3 gluon form factor for the experts, that you can get up to, I think it's 7 loops now, which is pretty impressive. The number of terms here I have written down somewhere. No, many pieces of paper, but it grows very, very quickly. I'll try to. Let's see. Many pieces of paper. Yeah. By the time you get to the 7 loops, there's 92 million, 92 million something terms where there's in the sum. So it's a very, very large, and the way that they found a lot of it actually is essentially this oracle thing, where it's some kind of not totally brute force, but they basically guess a whole bunch of solutions with some kind of smart sampling strategy, and then they check things. And then early on, they can just explicitly calculate everything, but some of the times they are able to use these guesses to make progress. Okay. So then let me say a little bit now about this kind of research. So on the AI side, there's been some recent progress with mainly by my collaborators. This is where I started. This is Lance Hay and gave a talk here, and he's been saying for a while he thinks maybe AI would help. Separately, I'm on sabbatical and I'm visiting scientist at Meta/Facebook AI, and there's a group that's led by François Charton, who's was here last week and would have been here if the talk was happening, but fortunately had to reschedule. 2201.04600. But basically what they did is they took a bunch of example recurrence relations like what you see in this OEIS database. So these are simple kinds of recurrent sequences, recursive or whatever. And so they generated their own. They just made up a bunch of random examples of recurrent sequences, and they also used all the ones that were known inside of that database, right? And so with that, they were basically able to come up with a way to sample them, and they know what the true formula is, right? So they have examples like, a to the n plus 1 equals 3a n, plus cosine of, a to the, n minus 2, over, 6 or something like that. I don't know, I'm just making something up. So the recurrent sequences, they could look back some number of steps. They have some sort of set of operations, unary and binary operations. So this is a unary operation that takes in an argument. This is a binary operation that takes in 2 arguments. Divide is so you can re-express this as like a tree, and the internal nodes are functions, and the leaves are either numbers or references to previous steps in the sequence. And so there was nothing numeric happening here. This was all symbolic. And so they generated a whole bunch of these things, and then they came up with an AI model that basically learned to represent the distribution of these kinds of the distribution of these kinds of formulas. But the ingredients of the space of this thing is all discrete, right? It's like this this would be, maybe I should do, this is like divide, like the top node is divide, and you have 6 over here, and then you have the numerator, which is a plus, which on this side is like a times, and a 3, and an a to the n, and this is cosine that the thing takes in whatever a to the n minus 2, right? So this is the tree form of this. And then you can similarly re-express this thing as some kind of like coded sequence, which I don't remember what the syntax was. It doesn't really matter, but it would be something like, divide, plus, it'd be like reverse Polish notation or something like that version of the tree. So you would have, times 3 a to the n, whatever, I'm just guessing at this point, cosine. Am I doing this right? It's been a long time since I used reverse Polish notation, 6, something like that, whatever it is. So you can turn it into a sequence, and then you use the word tokenize the sequence. Okay, so each one of these elements is a token, and so it turns into a sequence of discrete objects, and so you would so you have a distribution of sequences of discrete objects. That's so you reformulated this problem as like some probabilistic description of what's going on, and then you could do things like you can also then decode it and actually evaluate this expression if you want. And so then they have something where you can actually type in numbers, and instead of it being like a reverse lookup table, it's like basically based on those numbers, it makes a guess of what it thinks the formula is. And that's pretty cool, or you can give it bits and it will try to complete it. So this is related, I'll say a little bit about these kinds of models, but this is related to what's going on and what's called natural language processing. So for instance, right now, if you ask Google to translate something from one language to another, you would think that it's based on some sort of algorithmic rules or something like that. But right now it's using the same kinds of machine learning models that take the text and they tokenize it. And then what's also pretty amazing is that it can translate from one language to another without being trained on what's called parallel text. You don't have to have pairs of one sentence and its translated sentence. You just give it a whole bunch of English, a whole bunch of French. It learns how to, you have different sets of tokens for the words in English and French, and it ends up learning that each of these tokens will have a corresponding what's called an embedding. So it's basically some vector representation. So this would be an RD or whatever. So it's usually some like 500 dimensional vector associated to each word, and it will update where to place these words in this kind of totally arbitrary space, so that things that are semantically related to each other get kind of clustered in one area, and things that aren't are clustered in a different area. It seems super ad hoc and weird. It works amazingly well. So here's just one. So the types of models that are now so once you start to express this, there are lots of tasks. So some of them are called sequence to sequence tasks. I don't know how I'm doing on time. Sequence to sequence task. So the idea is you would get like an input would be, how am I on time?
15 minutes.
What's that?
15 minutes.
I'm over 15 minutes?
You have 15 minutes.
Okay, thanks. Oh yeah, okay. So sequence to sequence task, you would give it like, for instance, a sentence in English and say translate it into a sentence in French or something like that. And so it will look at all the tokens or all the words in the original sentence, and then it will start trying to produce one word, and it usually does it one word at a time, the translated sentence. So here's an example that I have here where it says, the agreement, the bottom is, the agreement on the European Economic Area was signed in August 1992, period. And then there's a special token called end, which says like, don't keep going. Okay, so that's also a token. So the sequences can have variable length. So the distribution that you're describing is kind of weird because it's not like a fixed data space. It's got variable length. And then so this is the input, and then the model will then start to output tokens that it thinks are reasonable. So the first one here, it's in French, and it produces l'accord sur la zone économique européenne a été signé in août 1992 period. So whatever. So, but what's a little bit interesting is in the process of doing the translation to these lines, if you can see, there's an idea where, okay, you have input sequence here, and now that you ask the model, okay, produce what you think the first word is. And so basically, you have if you had what do I want to say? If you have a probability distribution over like token 1, token 2, token 3, token 4, let's say we were always going to make sentences that had 5 words in them, and T is like the first word, T2 is the second word, etc. You can always write this without loss of generality as a probability for token 1, then times the probability of token 2 given token 1, then times the probability of token 3 given token 1 and token 2, dot, dot, dot. Okay, so this is without loss of generality. You can always write things that way. So then when in practice, then it's like, okay, I'm going to sample token 1 from that distribution, then sample token 2 from this distribution, sample token 3 from this distribution, and it comes into a question of, okay, how am I gonna model these distributions? And that's where the machine learning model does its thing. So when you do that, you could get lots of, if you ran the thing again, it's random, so you could get a different sample for token 1. Okay, so you sample token 1, and then you're going to sample token 2, given token 1, so there's a connection there. But when you're doing that, you also are going to pay attention to the entire input sentence, right? You're not wanting to just, I guess in this situation, the way I described it, this is a distribution over token 1 through 5 with no context. But I guess what I should have said is like insert a given a bar for given some context, and the context here is your input sentence. So you give it the input sentence, that's your context, and you say, now given that context, what do I think the distribution of like possible French sequences of French words is? So this would go. So this context would also go in here, and then there, etc. So when I go to generate token 2, it's going to pay attention to token 1, but it can also pay attention to all of these words down here. Okay, and so but that, and that's what these lines are. The dark lines are basically saying how is the model paying attention to the input words. That if it was a one-to-one translation and all you had to do is like know what's the French word for economics or something like that, it would be a simple problem. But you also need to rearrange words and phrases that sometimes have like it's like a 3-word phrase that's just said in a different way. And so if you're over here and you're wanting to produce this particular word, you have all the stuff you've produced up until then, but then there's this idea of attention where you're going to kind of pay attention to each of these input words in the context with some sort of like a weight associated to it. So there's this idea here that's called attention. It's pretty simple, really. So each of these words it's a discrete token, and so it has an embedding associated to it. So I'll call that like a hidden state J. And that thing sits as like some vector in d dimensions. And so the idea is that you want to take all of this stuff, pay attention to the whole sentence, and then turn it into I'll call it a C here, which is this context, or if I'm on like word I. So the idea here is that the context for word I is going to equal a sum over alpha ij hj. So hj are these embeddings or representations of all the words down here. So this is my j index. My I index is up here. So when I'm trying to decode word I I'm going to look at all the words in my input weighted by something. And then this is sort of, such that I want the sum of my alpha ij's, my sum over j, to equal 1. That's kind of arbitrary, but it's just to like normalize things. So you sort of like, you have a total attention, which sums up to 1, and you want to distribute it across the inputs. And this is just a way, and the C, is also going to be some vector in RD, okay? So you just have a bunch of vectors in RD. They're like abstract representations of words, and you're going to average them essentially in some kind of ad hoc looking way. And now the question is, how do you compute these alphas? So, so there are different things you can do. The first versions of this use little neural networks to try to figure out how you should pay attention to them. But the way that they're done now is, I won't bother writing the equations, but it's literally just like a cosine angle in the space. You say you have like you're decoding this word so that the alpha ij. Well, one thing is it looks like it looks like Boltzmann equation or something, or like you have a e to the minus beta over the sum. So j. So one thing is the way that you make them sum to 1 is just a simple rescaling, and then the question is, where do these betas come from? And the betas, I won't spend too much time, but basically you say this word right here also has a hidden representation I, and you do essentially a dot product between something like this word and each of the words down here. So it's sort of like if they're close by in this space, then they're highly related, and so you should pay attention to them. And if they're not, you don't. And it's again seems totally ad hoc, but you just give it the structure, and you're like, this is the structure you have to work with. And then when you optimize the model, it has to place them in this totally arbitrary space to make it work. Right? So you kind of give it some structure, some architecture, seems ad hoc, and then you train the thing to work. And when you train it, the way that you do it is just maximum likelihood. Like you have a probabilistic model. And so you say, like, I had that one English word that was like the input context. And then for instance, in some examples, like what should it translate into? And then you just evaluate the probability that it's going to produce that sentence. And it has a bunch of parameters which are essentially related to these betas. And you optimize those parameters until you maximize the likelihood. So in that sense, it's very principled. The current state of the art model, like there was one that was released last week, has 175 billion parameters, which is totally ridiculous, but that's the case. So I only have like 10 minutes left, so let me get back to the transformer part. So this kind of model, like roughly, I've only sketched it, it's called a transformer. Sorry, right when I'm close. Oh. Okay, but one of the key ideas is attention, and then this like sequential decoding, and the fact that it's trained on maximum likelihood. Those are like the takeaway points on the machine learning side. So in terms of the amplitude side and where we sit, and then I'll stop. Let's see, do I stop? Sorry, I should have. I talked about these, right? So what we've done so far is Lance has taken these examples where they've already calculated things up to 7 loops, and he sends us text files that have like 92 million coefficients in them. They're all integers, so that makes it nice in the sense that there's a discrete set of things floating around, so each of the the integers themselves, it's kind of crazy. The integers themselves have like a high dimensional embedding associated to them. But then what I didn't really talk about is that these functions right here, there are, that in the scattering amplitude, there's some kinematics going on, right? So that the right answer has to be formed in terms of like Lorentz invariance and stuff like that, right? So there's some number of independent Lorentz invariants floating around, like Mandelstam variables. So you know that the answer has to be a function of those things with some coefficients, and there's some more desiderata, but not a lot more. And then the structure of these but whatever, the types of functions you run into and these multi-loop things are polylogarithms. I had some notes on that, and I'm not gonna say, I don't have enough time to say much really more about them. But they satisfy all sorts of, there's these weird symmetries, there's a shuffle algebra, and all these kinds of, there's a dihedral symmetry, there's all sorts of structure that's in there. And anyways, this transformer model doesn't know any of that. We just give it a bunch of examples. Part of the problem is that there are going to be a lot of redundancies because there are all these symmetries that are going. So the same coefficient basically is represented many, many times. And it's not really a new degree of freedom. So we work with them to basically try to eliminate as many of those redundancies as possible. So we're kind of left over with like the core independent parts. But this thing right here, these functions will be, they're, what do I want to say? They're essentially polynomials or tensor products, whatever, but like they're tensor products between a discrete set of letters and an alphabet. They're literally like A, B, C, D, E, and they're all related to Mandelstam variables and stuff like that. Okay, but these so in the case of n equals 4 super Yang mills, there are what is it? It's just 6 letters, I believe, that you can work with. So those are, have discrete tokens to them as well. So in the model, we will say like, you're on this particular term, which is sort of like which term in a really big polynomial, what coefficient do you think should go there? And so the thing that's a little, okay, this part I want to say, and then I'll stop, is that the way that the data gets structured, especially if you want to go from one loop level to the next, is kind of like a high-dimensional version of Pascal's, triangle or something. So with Pascal's triangle, you have like 1, 1, 1, and then you the 2, and then I'm talking about binomial coefficients, etc. Right? So this is sort of like going to different loop levels. And you can think of this, this if I have like, A plus B, to the, I'll call this, this is like my n row. So this is going down this way, A plus B to the n. When I expand this out, if I just, I know that the power on A and B need to sum up to n, right? So all I need to do is keep track of what's the power for A, and that's basically where you are in this table, right? If I did so, there's a generalization where I do something like A plus B plus C, plus D plus E plus F to the n, right? If I do that, it doesn't. I need to keep track of what the power is on A, B, C, D, E, and then the F is implied, right? So this arranges itself like a 1, 2, 3, 4, 5. Yeah, okay, I should add one more. There's a G. It arranges itself as a 6-dimensional table, which is kind of like the generalization of this thing, So if I tell you, this table has indices, so if I pick up an entry in the 6-dimensional table, I'm telling you how many powers A, B, C, D, E, F, and G I have, right? And then I want to basically just tell you what is the integer coefficient and its sign. And what I would ultimately like to be able to do is bootstrap from one loop to the next loop, because there's some kind of recurrence equations that say that this number is a function of the stuff before it. And anyway, so we started to do that, and the first results that we got, which were pretty interesting. I'll kind of end with this. This is ongoing work, but this is like training time, train time. And this is like accuracy of predicting the coefficient at some loop. In this first example, we didn't even try to predict it, giving it information from a previous loop. We just worked at one loop level. And so at first, the accuracy of the model is terrible. It can't predict them. And then it starts to get better and better and better. And then it kind of plateaus. And then after a little bit, it turns back on again. And then it plateaus. And what we see that's kind of interesting is that at this point, it has no idea what the sign should be. Like the sign is like totally random. So That's why there's a plateau here, and then this plateau is basically twice as big. So once it gets good at picking out the numerical, the absolute value of all these integers, then it starts being able to figure out the sign. So it's somehow like there's a, like if you knew that all the numbers had to add up to 0, then like you would be able to figure out the sign once you've been able to figure out all the absolute values, right? So some kind of phenomena like that's happening. It's totally random on the sign until it essentially nails that. And I didn't give you a scale here, but this is like basically very, very close to 50%. And then this is right now, we're at like 98, 99% accuracy in predicting these coefficients, which is pretty cool. But this is
it's one loop, and how many external legs?
So this, for this example, this is the 3 gluon form factor, and we've done it at a few different loops, but I think this data set was something like I forget if it was the 5 or the 6 loop. We didn't want to use all of the data that we had so we have more room to play. But this is not really, this was like the first result, which was pretty interesting. The problem is you could not carry this out at the next loop because we don't know the answer. Like this week only worked because we knew the answer at that level. So the next thing that we're trying to do is that there are these rules that, because of the recursive nature of it, that if you're on some symbol, like, say, I'll just make something up here, A, B, C, D, E, F, G, you know that it's made from basically like a product of symbols below it that are missing 2 of the symbols. So it's got to be something like A, B, C, D, E, it has to be something with 2 less things, and then another one with 2 less things like C, D, E, F, G. It's some kind of, it's related to products and things like this. And so what we're doing now is like saying, okay, I want you to predict the coefficient that goes in front of this term, and in the same way that we did over here, you can access, you have available to you the coefficients that were at the at the previous loop level with kind of the right ones, and that is also predicting at the kind of 99% accuracy level. So that's something that if that rule that it learns extrapolates, which we don't know at this point, then if that really worked, it's like basically learning, that this is trivial. What is the rule that predicts this? You just take these 2 and add them together, right? If you can learn a rule and that rule abstracts, then you can predict the rest of Pascal's triangle, right? So if we can learn the rule that relates, the entries in this 6-dimensional table so that they extrapolate to different loop levels, then you basically solve that problem to all orders, right? So we can't say that, but like the first steps are pretty promising. So that's where we are. Yeah.
Are there examples when your machine-generated laws are used, like in analyzing LHC, for example, or in analyzing cosmic rays? Or is there an example where people believe that this black box approach is superior to standard methods of computing?
Yeah, I mean, here it's kind of weird because we're talking about like symbolic stuff and more like equations. When it comes to like at the LHC for analyzing data, and you want to say like, do I think this energy deposit in my detector is an electron or a photon? We absolutely use machine learning all the time for that. But the thing is that at that stage, you can also you can just like many other ingredients in our experimental apparatus, we think we know how they work. We're not 100% sure how they work, but we can use data to just characterize their properties, right? So
are you saying these machine learning methods are actually used to analyze LHC data?
Yeah, absolutely. Yeah, but they're not of the style so much that I'm talking about, but they're not like wildly different. But you have in some sense, it's a black box that you give it like energy deposits in a bunch of parts of the detector, and it outputs I think it's an electron or a photon, and and then we characterize the efficiency that it does that, and how sensitive it is to like miscalibration of detector components.
But then how do you know that your machine is not cheating or something? Like, how do you test it? You test it somehow?
Yeah, that's what I'm getting at. Is that the only reason we use it is because we have all sorts of ways to like empirically assess and characterize the performance of that black box. So we can take control samples where we know that there are electrons and we know that there are photons because you know, some considerations, like it makes a z-peak, you know, so we know that those are electrons from the
So
z-peak.
you're saying whenever you can test it, it seems that it is not cheating.
Yeah, yeah.
And
Or, you
then
know,
you
I
just
mean, in
trust-
some sense, cheating, not cheating, whatever, it's a function, it's doing
But
something.
if her intelligence is now superior to yours, this
Yeah.
is what you are saying, how do you know it's not cheating?
Yeah, well, I guess I'm just saying, like, in some sense, it's like, yeah, I mean, it becomes a question of what do you mean by cheating? You know, like, it's getting there through some means that you don't really know.
She's now smarter than you are, so why wouldn't she just play games with you or whatever? How do you know?
Right, well, I guess there's the best function that I can come up with to try to separate electrons and photons. And then there's the one that, like, this machine learning approach comes up with. But then, so now I have two functions, and I can forget about where they came from, and I don't have to interpret what they're doing. I can just think of them as sort of black box, as long as I have a way of characterizing how they work experimentally, right? So now just like all sorts of pieces of electronics, I think I know how they work. I think I know how resistors and transistors work. But there's, you know, unknown amounts of electronic noise. They're working in a high radiation environment. I don't trust that my simulations of how a transistor in a high radiation environment work. I measure it in data.
You are saying this situation is not really unique,
Yes,
that we have
it's
to
not unique
trust
at all,
some,
exactly,
right?
yeah.
Right.
But when you get to some of the things here, you start to transition from that kind of stuff where you can turn it into a very operational question about how you characterize it with data and characterize systematic uncertainties to things that are more like, do you understand what's happening? And that gets to be kind of weird. So, I mean, I think this starts to have a qualitatively different feel to it, you know.
So back at Slack, when they were using bubble chambers or cloud chambers, there was just a room full of people who would look at photographs of the tracks and decide what particle it was. And those people had learned this from experience of seeing many of these pictures, and there was no way to know.
We are saying there is nothing unique again.
Well, now it's a
We have been doing some such thing for a long time.
Radiologists look at
And
scans and decide.
I mean, we have done it, and even much worse than machines. I mean, we have seen Jesus faces in Idaho for centuries, right? So probably this machine wouldn't do that.
Yeah. Real cheese sandwiches.
Just to understand what you're doing in the amplitudes a little better, you're not giving this any physics input, right? You're just having it predict amplitudes based on patterns that it picks up?
Yes and no. So at some point, we don't know how to give it more physics input, and then it's just doing patterns, and that's where it's kind of this probabilistic thing. If, for instance, we knew that there was like a symmetry, like this probability has to be the same as if I switched 1 and 2, you know, then I could try to figure out, can I construct a model that enforces that symmetry? And that's a whole interesting active area where you try to figure out how to incorporate your domain knowledge into the machine learning models. The other approach there is you just remove that symmetry by like changing how you represent the data. So you just would mod out that symmetry. And so currently that's what we're doing. We don't know how to incorporate the symmetries that we know exist in the coefficients into these kinds of models, but we know how to basically mod them out so that we're only working with like a reduced form of data where that redundancy is not there.
So this was in equals Fourier mills or in regular mills?
This is an equal 4.
At large n or
I believe so. Yeah, like this is all very recent, and it's also while I've been like doing 10 other things. So we just kind of started going, and it's like there's a part where I'm trying to help facilitate discussion between François, who's running experiments and etc. So there's lots of details that I don't know, and I'm also kind of coming up to speed. But so there's parts of it that are more where my role is more mechanical than I would like it to be, but I'm catching up.
So I'm just asking because large n supersymmetric mills is probably integrable. So there's infinitely many conserved charges, and it's not crazy that an algorithm could find some pattern.
Yeah, no, there's definitely like an integrability constraint that shows up. I don't know if it's I'm not 100% sure if it's the same notion of integrable you're referring to.
It's a theory that probably has infinitely many conserved charges. And so it's conceivable that you could find a rule, an algorithm or something that would just output every.
Yeah, I mean, it's so highly constrained mathematically, it's not surprising that there is such, and I didn't say it, but like, here, if you wanted to like walk through, like say you always asked like the one is obvious, but like say you want to know what's the sequence of just off by one. Like you can imagine you could come up with some recurrence relationship pretty easily. In the 6-dimensional tables, if you walk through certain, like along the edges of this table, the kind of the equivalent of doing this, but in a higher dimensional table, there's a few different ways to walk through this thing where they have recurrence relations that have checked to every order that they've gone through, but that's only like little slices through this big table of coefficients where they know what's going on. And so the goal here is, can you basically explore them all? And that's not known currently. So
There might be a big difference with ordinary angles, which is not a
no, I mean, I agree. I think that there's a part where, like from, I think Lance would probably say that like this is kind of like a theoretical playground to start to develop a lot of these kind of mathematical machinery, and then you hope from there that. But I agree, it's not. As you go to more realistic things, there's lots of that structure starts to disappear. The problem gets harder and harder. So yeah, so I'm not saying that this is gonna we're gonna solve like normal QCD tall orders or something anytime soon.
They do have amplitudes for real QCD, even though they're lower order. Do you know what is the state of the art?
Yeah.
Last of those, but for real QCDs.
So I had I might maybe even have it in reference here, but it's not very high. Like it's like for there's a claim in what like Lance was writing that what depends on how many legs you're talking about, but it's not big. I think it's like basically one loop for anything that's like 3 or more muons or something like that. And so there's a phrase that he has in there is basically in this situation you can do things to sort of 6 loops more than you can do in real QCD. So I can give you the precise answer right afterwards though.
Let's thank Carl again.
So Massimo, what does the origin?
So the
of
story
the
is that,
bootstrap?
the time machine, there is a big set of